I've given us a vector function here. V of t is 1, 2t. I've purposely named it v of t because I'm going to be thinking of it in terms of velocity. I'm trying to wrap my head around what a definite integral means. And I have a sense of what I'm supposed to get if I integrate velocity. Because if I integrate velocity as a real valued function, I get displacement. So I'm hoping that it kind of makes sense in this case as well. Okay. So we're going to approximate the definite integral from 0 to 1 of v of t, of our velocity function with respect to t. We're going to use a Riemann sum. N is going to equal 4, so we're using 4 rectangles. I said to use a regular partition. All that means is that we're going to be chopping the t-axis up into equal pieces so that delta t will be the same for each piece. And then for our representative t values, we're just going to use the right endpoints of those intervals. Okay, excellent. And let's just, again, so that we can sort of contextualize this, let's think of this velocity function as being measured in meters per second. Okay. All right. So the first step is to chop. Now I'm just doing the first 3 steps. I'm going to chop, approximate, and add. That creates my Riemann sum, which will approximate the definite integral. We're not going to be taking the limit of our Riemann sum, which would give us the exact answer. Okay. So the time axis, we go from 0 to 1, and we're chopping this up into 4 equal pieces. So of course, each piece is going to have a value of delta t would be just 1/4, would be the length of each subinterval. And my endpoints would be 0, 1/4, 1/2, 3/4, and then 1. Okay. All right, now what I need to do is from each of these intervals, I need to choose a representative t value, and I'm saying we're going to choose the right endpoint. I'm going to need to evaluate my velocity at that point, and then scale that by delta t. So I'm going to just create a table of values here. I'm going to list our t values. I'll just write. Let's actually keep track of our index too. So, whoops, we'll have our index. So that's just counting from 1 to 4. First interval, second, third, fourth. Okay. We'll list our ti star, which is our right endpoint. We're going to evaluate our function at that point. And then we're going to scale that by our delta t. Okay, so for this first subinterval, my right endpoint was 1/4. Oh, and I'm sorry, I called my function v, not r. I initially wrote those as r's. Those should be v's because that's what I chose to call this function. Okay, so if I evaluate my velocity at time 1/4, I'm going to get 1, 1/2. And now if I'm scaling that by delta t, my delta t is just 1/4. So I'm going to get 1/4, 1/8. Okay, for the second subinterval, my right endpoint is 1/2. You'll notice I've just drawn a picture of the t-axis here. I didn't draw v of t. That's because when I'm drawing v of t, I don't actually draw the t-axis, but I needed the t-axis to see what my representative t values would be. Okay, so 1/2. When I plug that in, I'm going to get 1, 1. When I scale that by 1/4, I'll get 1/4, 1/4. For the third subinterval, my representative time is 3/4. When I evaluate the velocity at that time, I get 1, 3/2. And when I scale that by my delta t, my quarter of a second, I'm going to get 1/4, 3/8. All right, and then for the fourth subinterval, my right endpoint is 1. So when I evaluate my velocity there, that's going to be 1, 2. And when I scale that by 1/4, I will get 1/4, 2/4, or 1/4, 1/2. Okay, so these are the vectors that are going to occur in my sum. My Riemann sum is just going to be these 4 vectors added together. Let's see what we get. In the x component, we get a fourth, a fourth, a fourth, a fourth. That's going to give me 4/4, or 1. And then in the y component, let's see, that's 1/8 plus 2/8, so we're at 3/8, 6/8 plus 4/8, that's 10/8, which would reduce to 5/4. So this is my Riemann sum, this vector 1, 5/4. Okay, we've done it. What does it mean? I am going to draw a picture of this Riemann sum. Now, I could just draw the result, the vector 1, 5/4, but what I'm going to do is I'm going to illustrate how we get that result by adding things. So I'm going to just, here's my x and y axis. I've only drawn quadrant 1 here. I'm going to put this vector in standard position. So let's see. 1/4, 1/2, 3/4, 1. Looks like on the vertical axis, I'm going to want to mark off my eighths. So I'm going to use the same scale. This distance is still 1/4, but I'm putting tick marks at every eighth. So okay. So the first vector in my sum was 1/4, 1/8. So if I draw that in standard position, I'll come over a fourth, up an eighth. There's that first vector in my sum. Now the second vector in my sum is 1/4, 1/4. Now I'm going to draw the vector addition, which means the vector I'm adding, I'm going to put its tail at the tip of this first vector. Okay, so we're going to come over a fourth and up a fourth. So that's going to put me right there. Now the vector that takes me from here to here would be the sum of the first two terms. I'm going to wait to draw in the result until I've got all four terms. The next term I'm adding is 1/4, 3/8. So I'm going to put the tail of that at the tip of this vector. We'll go over 1/4 and we'll come up 3/8. So we're about there. And then I'm adding 1/4, 1/2. So I'm coming over 1/4 and up 4/8. I think I actually came up a little too far there. It'll look something like that. And then my Riemann sum is the resultant vector. This vector in blue is my Riemann sum, 1, 5/4. Now, we said we were trying to estimate what we got when we integrated velocity. And we know with real valued functions, if we integrate velocity, we would get displacement. Does it seem like this is estimating displacement? I think so. Because what we did is we picked a representative velocity. And we said, let's just, oh, our velocity is changing. That makes things difficult. Denial. Let us pretend that the velocity does not change but is constant. And let us follow that velocity for 1/4 of a second. But then, let's acknowledge that the velocity actually is changing. So, before we go into denial again, let's reassess. Let's pick a different velocity at a later time, and let's follow that for 1/4 of a second. And that was this vector. And then we reassessed. Now what's our velocity? Let's follow that for 1/4 of a second. Now what's our velocity? Let's follow that for 1/4 of a second. Okay. So, for each one of these legs on my Riemann sum, we were essentially estimating the displacement over that particular 1/4 of a second. We add them together, we've estimated the displacement overall. If I wanted a better estimate, I would use a shorter time interval so that I'd be approaching taking the limit as my delta t went to 0. Okay. So that actually does make some sense. And if I were to actually integrate from 0 to 1, our velocity we said was 1, 2t dt. Now we've said this is defined to be the limit of a Riemann sum. Okay. But you'll notice that as I was doing this, I worked with each component individually. And we know with real valued functions, when we take the limit of a Riemann sum, that's equivalent to just taking an antiderivative and evaluating. The fundamental theorem of calculus gives us that. Now, if we take derivatives component-wise, it would make sense that we would take antiderivatives component-wise, and that the fundamental theorem of calculus is going to apply here as well. I would simply say this is going to be an antiderivative of 1 is t, An antiderivative of 2t is t squared, and I'd evaluate that between 1 and 0. And so that would give me 1, 1 minus 0, 0. That would give me 1, 1. Now, that's the true displacement. What we got was 1 5/4. It was close. Wasn't super close because we only used a Riemann sum with 4 vectors instead of with lots and lots of vectors in very, very short time intervals. But I can see this was actually estimating the true displacement, which would have just been this vector right here, stopping at a height of 1 instead of going up to 5/4. Okay. So, definite integrals are limits of Riemann sums, but the fundamental theorem of calculus allows us to evaluate them by simply taking antiderivatives of each component.